plane area by calculus, Green's theorem, and Monte Carlo integration. Recently, Scott Gould, college physics professor at Claremont McKenna, Scripps. These are members of the Claremont group of colleges in California, and they share faculty and courses. So his name appears in more than one place. Here is his webpage at Claremont McKenna. So you can see here the URL. He's on the faculty, listed on the faculty there. And here is his webpage at Scripps. So he's in more than one place. He's also a frequent responder to queries on MaplePrimes. And one night he asked me if Maple could do Monte Carlo integration. And I remembered seeing Monte Carlo integration in Maple. So I looked it up, and it's a NAG method. And it's under this numerical integration help page. And it's down here, method equals Monte Carlo. But there's this proviso. These methods are for multiple integrals over a hyperrectangle. So it's not going to apply to this figure, which is the one that prompted Scott's question. So I remembered that there was a discussion on MaplePrimes, and it appeared more than once, attributed to this author, Kitonum, describing how to use Green's theorem in the plane to compute the area of an irregular plane region. Now, while I was playing with this problem, I got an email from Scott, who had created a video presentation for the Monte Carlo code that he wrote. Well, he created a video presentation describing that code, and I'll show you that in a second here.
In this video, I go over numerical integration. It covers a problem for which it is difficult to set up a mathematical formula or a set of data points to solve for the area within a region. It uses the Monte Carlo method, which includes a fair amount of coding. More numerical techniques and coding will be implemented in this series.
Now, Scott has a full YouTube channel in which he has created a number of Maple-related videos.
Do you need to learn Maplesoft's Maple? Do you need a refresher on how to use Maple? Learning Maple is a video series to help you maximize your productivity using Maple while minimizing the amount of coding you need to learn.
So these links can be obtained if you ask for this worksheet. Here's my email address. Send me an email, say you want the worksheet. I'll send it back to you. And then you don't have to go hunting for these various links. So at any rate, I'm going to show you this stuff that Kitonum provided using Green's theorem. I will also show you how I calculated the area with basic calculus. Then I'm going to take a look at Scott Gould's Monte Carlo code. Figure 1 shows the area that we're trying to compute in this example. This is the unit circle centered at the origin. These are circles of radius 1/2. The center of this leftmost circle is at -1, 0. And this is an equivalent circle whose center is at 1 over the square root of 2, 1 over the square root of 2. Let's look at these posts from MaplePrimes going back to 2013. So this is the first post by Kitonum with his codes for doing these kinds of computations based on Green's theorem. You'll see these three codes. This one computes the circumference or the perimeter. This one computes the area. And this one draws a picture. Now, as you scroll down here, you discover that something happened with these pictures. We'll see that fixed in a minute. In 2017, 4 years later, the issue came up again on MaplePrimes, and you see Kitonum's code appearing again. And now you see some of the pictures that he's able to draw, figures that he's able to compute the area and perimeter of. And I've got this worksheet rescued. 5 years later, the issue comes up again. And here's Kitonum's response on MaplePrimes. Here's a graph of this implicitly given function, and it's not capable of being solved for either x or y. So here's some discussion back and forth. Here's Kitonum's code showing up again. And what he did was to pick a number of points and approximate this figure with little line segments, and then he applied his code to that, and he gets what's essentially a numeric approximation. Now you'll notice over here, after the second appearance of Kitonum's code, I had a post MaplePrimes in which I deconstructed that code for computing the area because I was just curious about how he went about doing that. I was so intrigued that I said, I'm going to write this blog. And when I realized, he's computing flux because that's what Green's theorem says to do. And I replaced his area calculation with calls to the vector calculus flux command, either for line segments or for parametrized curve sections. Then there was an extended discussion of what was really going on. We will eventually take a look at the code that Kitonum wrote for the area via Green's theorem more shortly. Let's initialize so that we can do some Maple. I'm going to draw pictures. I'm going to use plot tools to draw pictures of circles. I'm going to need student calculus 1, the vector calculus package, and whenever I use vector calculus, I always have my vectors represented as column vectors. I solved this problem with elementary calculus techniques just to see how difficult that was going to be. And so the very first thing you need to do is represent the circles. So the unit circle here I call C1, 1 over the square root of 2 I called A because I didn't want to have to keep typing that. So this is the circle on the upper right, and this is the leftmost circle, just represented in Cartesian coordinates. Next, I zoomed in on this section of the figure, and I also realized these two handles were similar. So I looked at just the leftmost handle. Let's close this. And drew a working figure. It'd be nice to have all of that in one image. Okay, this is the leftmost circle. This is a piece of the unit circle. See, here's the center, -1, 0. And I drew this vertical line. So I need to know this x coordinate. And then I integrated from 0 to this circle and 0 to this circle. Those are two elementary calculus problems. The hard part is just figuring out what this x coordinate is, and that's just an issue of a solve command. So having drawn that figure and said, okay, I have symmetry, I get area here and area here, and then double that because of the symmetry between here and here. That's how I went about working this problem. Well, we need the intersection of these circles. So I do that calculation here. It's a question of a solve command. The intersection of circle C1, which is the unit circle, and C3, which is the leftmost circle. There are two intersections, clearly one here and one here. And it is this x coordinate that I really need. That's at -7/8. So that's -1. This is -7/8. All that remains is to actually do the integration. There are two integrals to compute, one on the left of this red line and one on the right of that red line. Now, this result is the total area. The area of the unit circle is pi. If you just slap on the area of the two smaller circles, you will have a number that's too big. But what is the area of one of these smaller circles? Pi r squared, r is a half, so it's pi over 4. You double that, and you've got 3 pi over 2. That would be the total area, and it would be incorrect. You have to subtract off this overlapping stuff. And remember, we have this amount 4 times, and this amount requires these two integrals, -1 to -7/8, and -7/8 to -1/2. Don't let this 0 fool you. That's there for the vertical axis. You've got a radius here of 1/2. This is -1. This is -1/2. So this is just integral 0 up to y, 0 up to y. Maple does this very nicely. It gives this exact expression, and if I float it, I get this approximate value, decimal approximation. And so that's the target number I'm using to actually get my hands on what is the value of the area of this figure. So let's do a very quick review of Green's theorem and how it relates to plane area. We'll close up some of that stuff. Okay, let's refresh our memory. On Green's theorem, f is a vector, two components, f and g. This is the divergence of this vector field over this plane region R. It's equivalent to a flux integral because whatever diverges inside the region has to pass through the boundaries. So you go around the boundary and you measure the normal component. Normal component, that's the flux. If G is 0, then your vector is x0. G is 0, this drops out. You go around the boundary f dy. It's a flux integral. It gives you the area inside. So now the nitty gritty of using Green's theorem to compute area of a region, plane region. So here is a comparison. Kitonum's code for just computing the area and a little bit of modification that I came up with to use vector calculus. So what Kitonum does is first represent the boundary as a list of lists. Each sublist is either two endpoints of a line segment or a parametric representation of a piece of a curve. And that parametric representation has an x and a y, and the bounds on the parameter. Well, then he goes through that list of lists and he integrates int, you can see here, int, the appropriate integral, and then he adds up all those bits. And here he's integrating the other kind of element in that list of lists, which is what I've done here. Flux. It's either a line segment or a path integral on a segment described parametrically. And so that's the only difference between these two blocks of code. Now, because the early code written by Kitonum and posted to MaplePrimes going back to 2013 did not behave itself. The figures were missing. He had this worksheet. So I grabbed this worksheet, had to fix a few things to make it work properly. And you see perimeter procedure. This is the procedure he used to calculate the perimeter of a plane region. And remember, each time it's this list of lists used to describe the figure. This is the one where he computes the area. And this is the one where he draws a picture. And then he gives these examples. So this is the list of lists that describes this first figure. This is what the figure looks like. And this is just the boundary of that figure. Here's a second example, list of lists that describe this thing. And it's just a list of endpoints for line segments. A third example, the region between a sine and a cosine. A fourth example is this star-shaped region. And a fifth example, you can see how it gets messy as you have to describe these intersections and the arcs that the intersections cut off. It's kind of like the three-circle example we're doing, only the different size circles placed in a different location. Anyways, he had this worksheet included, so he gave you the pictures that were missing from that glimpse at the old MaplePrimes post. So let's implement these kinds of calculations for the problem that we're facing. So we begin looking at this figure 3. Unit circle and these other two circles. And because I'm going to rely on symmetry, I now started to look at this region. And if I'm going to compute the area of just this region, I'm going to have to parametrize arc L1 and arc L2. And to do that, I'm going to need these intersection points called P1 and P2. Well, I need to solve for the intersections of circle C1 and circle C2. That will give me these points here and here. Well, this solve command returns two solutions, x, y, x, y. This trick pulls out the x and y values without the x equals, and I can call this list P1 and this list P2. And then I need the angle for the parameter t along that arc. And so I compute an arctan and an arctan yx, yx. These are the two angles exactly, and these are the two angles as floats. And so as I integrate along this arc, the bounding values of the parameter are these two numbers or these two exact values here. So let's look over here for parametrizing arc L1. X and Y coordinates on this arc, that's a circle, piece of a circle. A, remember, is 1 over the square root of 2, which is the center, and I'm using polar coordinates. Cos, and notice my use of some number, some name like u to be the parameter. Divide by that's the radius 1/2. Okay, so here's the x and y, and I want to solve for these 2 points in terms of the parameter u. So I set these points equal to x and ask for the value of u. Well, this one here comes out okay, but this one gave me some trouble, and it was until I realized I needed to go below 0, to the left of 0, and go from minus pi to 0 to get this value of u that I was not getting the answers that I needed. And so x in terms of u, y in terms of u, value the parameter, and if I float those values, you'll notice it's from minus 1.038 to 2.609, let's say, radians. And you'll notice here I use solve, but here I use the calculus 1 package roots command. That's because that allows me to put a range, even though I'm doing a solve. But you can't put a range on the solve command, but you can put a range on this roots command. Let's get the area. Pi is the area of the unit circle. I have two lumps, two handles. That's what that 2 is. And I'm going to obtain this area by integrating along arc L1 and then along arc L2. It's a flux integral. So my vector field is x0. Each case, my vector field is x0. This is the path u1 to u2. Notice it's from minus 1.0 something pi to 2.6 pi. That was the tricky part. The devil is always in the details. Okay. Now, as you come down arc L2, you need the parametrization from T2 down to T1. T2 down to T1. So Maple gives this as its exact answer to the area of the figure. Now, this does not look like the answer we got earlier when we did it with elementary calculus. And to beat this thing into the shape of the other answer is a nightmare. As anybody who has tried to do this in Maple knows, this stuff is just a nuisance. And so I simply floated the number, and these numbers match. If you were to subtract the two numbers and simplify, it would be 0. But to beat this into the form of the other one is just not worth the trouble. We now tackle the Monte Carlo technique. So this link takes us to what we saw earlier, Scott Gould talking about the Monte Carlo technique that he wrote code for. But I want to show you this link down here that gives a presentation of the code that Scott wrote. And this is cleaned up version of his code. And you notice he's interchanged the position of these two little dog ears. But here is his neat presentation of this Monte Carlo code. I'm going to show that to you in a worksheet format so that you can play with it if you want. Scott's code begins with definition of the circles. Here's how he represented the circles as members of table, and he included center and radius as part of the attributes of those table elements. So his figure is described by these table elements. Left boundary, right boundary, x boundary, y boundary, so that he can draw a graph. Minus Lx to Lx minus Ly to Ly. So he gets this figure drawn with plot tools, disk, and then he pulls out the properties of the circle, having stored all of that in the table. Nice coding device. So in the Monte Carlo method, you generate random points, and then you have to decide which of those random points fall inside the region and which don't. So here he's deciding how many circles is he looking at and how many significant figures is he going to make use of. So he's got three versions of this code. And the first code is just uh, proof of concept. Does it work? And he's got the code in a code edit region. Okay, we've expanded it. Let's take a look at what his code attempts to do. And he's broken it down into various procedures and so forth. Random points. He decides if a point is inside a circle or not by looking at the distance of that point from one of the centers. So he's got this distance function defined. And it's genius what he's done here is he's realized that if you test the point to be in a circle, one of those three circles, you up the counter and move on. You don't have to decide if it's inside one but outside the other or anything like that. If it's random point, check to see if it's in one of the circles and you go 1, 2, 3, circle 1, circle 2, circle 3. Soon as it's inside one of those circles, it's inside the region, up your counter, move on to the next point. I thought that was pretty clever because otherwise you have a real problem deciding is the random point in the region or not. So he timed this raw procedure and it runs 13 minutes and it gives an area of 4.12. We had calculated it exactly as 4.0 something. So then he moves on to improvements to speed this code up. In the second version of his code, he makes these changes. First, the distance function that he uses to determine if a point is in a circle or not is compiled, so he speeds that up. And the other thing that he does is he makes various quantities be of type or data type float. You'll see the time is decreased to 2.2 seconds and the value of the area is pretty much the same. Now, if you want to take a look in here, right click, expand. I think if you right click here, then it opens it up. And you can see the changes that it takes in the code to do the things that we just mentioned. Compiling, right? See, compile here. And the data type equals float here. And I think he's got another data type equals float here and here. Significant speed up in Maple's numeric calculations. Now, Scott's third version is the fastest because all variables are data typed float and the code is completely compiled. You'll see that the time is virtually zero, almost instantaneous. And the area is roughly close to what it should be. And if you want to take a look at this total compilation, expand this, and I think you have to right click on that. It opens it up, and you can see a lot of data type equals float everywhere. Data type equals float. And someplace down here you'll see where he's done the compiling. And that procedure runs in virtually no time at all. So, some very interesting techniques in coding, and if coding is your ball game, if that's what you like to do, then you can get some wonderful points coding from looking at what Scott has done. Uh, Interesting the way he decided if a point generated at random is inside the region. All he has to do is determine if it's in a circle. And you go through the circles in order one, two, three. As soon as it's in a circle, it's in the region. Uh, that's brilliant because if you try to figure out how to determine if a point is in an irregular region, you've got to fool around with lots of inequalities. So for this problem anyway, I just thought that was very clever. And I asked Scott the following question, neither one of us is content with our speculations. You generate a bunch of random points and you see which proportion falls inside the region and which falls outside the region. Why do you do that? Why do you do that instead of taking a uniform grid over the rectangle and you find out which of those points are inside the region of interest and which are outside? I don't know. I'm not that familiar with Monte Carlo methods, and I don't know why random points are used rather than just define a random grid over the region. Perhaps somebody out here in the audience knows.